Good morning and welcome to, hold on, let me turn up my volume in here. And welcome to physics, what is it? Physical Science 1, basically. We're doing chapter 8. Chapters 8, 9, 10, 11, and 12. So they're going to be basically put together for another exam sometime in October. And the content is a little bit heavy. That's why there are a few of them. So the idea is more or less similar. And then chapters 12 through 19 are going to be a separate exam. They are similar ideas to all of them, which is really chemistry. And then chapters 20 through 28, in between of them, we're going to skip a couple of chapters, are going to be the final exam. And those are dealing with geology and astronomy, basically. So this is basically what we're looking at. So this chapter is not tested this Tuesday, but the rest of the chapters are. Now the exam is going to start sharply at 8 o'clock and ends at 9:55. And to make sure that people who need to work, they can, the exam really needs to take an hour and a half, an hour and 25 minutes to be more specific. If you started at 8, by 9:30, I would expect you to be done. Probably some of you will take a lot less than that, maybe an hour, be done with it. And for some people who cannot start it early, they will start it at, let's say, for example, 8:30. Then they will be really getting it very close from the 9:55. So that's basically how the exam is planned. I will be available, basically. I will have this very same session open, just in case if there is a question or something is not working or something like that. And you would ask a question, of course. Don't ask it with a microphone, ask it only on the chat, because I will have the session open, but I will turn off my microphone and I will turn off the camera, and I will only have a headset on my ears, basically listening. But I would expect that the questions, if there are any, are going to be on the chat session. I will answer them also on the chat session. That way, basically, you have a feedback without disrupting somebody else who may be basically have the session open. Now, I suggest, you're not required, I suggest that you sign in also to the session, you sign in to the Zoom session. The reason why I would suggest that is, if let's say, for example, after 20 minutes on working on the exam and you discover that there is an issue that you encounter and that question basically you would want to ask, you look at the chat and the question was already asked, and I already provided the reply for it. So you don't want to basically go through the same struggle that the other person went through. You already have the answer right there and there. When you're done, you may log off. Again, it's not required, but it's a good idea to basically sign in into the Zoom session or log into the Zoom session and leave it open, okay? And monitor the chat, okay, from time to time to see what's going on, if there is something that is relevant to your case. And if it's not, then just basically keep on working until you're done with the exam. Does this sound correct? You guys understand what I'm talking about? I know a lot of you are not here and will be watching this later on. No, from 8 to 9:55, Jacqueline, not 9:50. Yes. Yeah, so the answer to Jacqueline is she wanted to know the exam is going to be open for a day or 2 days or 3 days. No, it's going to be between that time span, okay? From 8 to 9:55. That way it's done and we move on to some other things and we focus on the other materials. You guys understand the question? So I know a lot of you probably are not here. So even if you're working, this is the time where you need to at least take an hour and a half from your work to make sure that you get your exam done. And then you can resume your work. You can go back to your work and you can tell them that you're taking a class and you need to do your exam. And then after that, you go to what you need to do, okay? Does this answer your question, Jacqueline, now? Clarifies it? Okay, I will post, you will have further communications from me more specific to the exam, basically. and the timing and all of these things I was talking about. But this is basically just in case if somebody has a question now or from now until the exam day. Again, the review exam is on Canvas. I would suggest that again, Josh is asking if do we have to sign in? Of course, no, you don't have to log into Zoom. I recommend that you do though, okay? That's all. So if you choose not to, that's up to your, that's your prerogative. I'm not forcing you to do on that day. It's a good idea to do just in case if, again, a question is asked, that way you don't have to ask the same question again, okay? When you're done, of course, you can log off, and at any time you can sign off and you can leave. Yes? Josh and everybody else?
Got it.
Okay, very good. So chapter 8, as I said before, is not part of this exam. So, but we have to really take it seriously because at some point we have to get into it and tests on it. And it's a very important topic. So it's all about electricity and magnetism. Let me see if this is the chapter. I think this is the book. Yeah, chapter 8. Okay, so let me get from the beginning. So we're going to have maybe fewer questions today than usual in terms of the discussion. So there is a discussion after this chapter so that we have it, where we can go through it. So again, it's about static electricity. We were, as a human race, basically, from the dawn of time, basically, we're amazed with some electrical phenomenon, like, for example, lightning, the one that you see behind me. And of course, since we didn't understand it at that time, some leaders of ours at that time took advantage of it and associated it with mysteries and sorcery and all of the things like that. But people persisted and started experimenting with it and trying to understand it and see what it is that electricity is and lightning in particular is. And this is what emerged off of it, is the concept that we're going to discuss today. As a matter of fact, is so critical, our understanding of electrical phenomenon, that nothing today can operate without it. You're communicating with me right now and you're following the class thanks to the developments of what happened in this branch of science, which is electrical engineering and electronics, which are two different branches of engineering, but they stem from what we're going to learn today. So everything that we do as electrical engineers or as electronics, basically engineers, is coming from this field of electricity and magnetism, because it turns out when we learn later on magnetism, that electricity and magnetism are joined in the hip. Actually, they are one thing. It's like you have a quarter basically, and you're looking at it from two different faces. That's all. It's the same thing. It appears sometimes as electrical phenomenon, sometimes it appears magnetic phenomenon. But that's basically what this whole idea is. So everything we have today, from cell phones to computers to TVs to microwave ovens to coffee makers to watches, smart watches or dumb watches or whatever you can think of, cars, everything is really powered by this branch of science. So we have to really have an understanding of it. So the first starting point in here is, where is my pen? Oh, here it is of course the concept of a charge. Okay, so we really have to understand what the charge is, what the electric charge is. This is the foundation of everything. We will learn specifically that the whole thing in terms of our daily experiences is governed by a specific particle called an electron. Okay, so the electron is at the foundation of everything, and due to some unfortunate, accidental, if you wish, event that happened in the history, we appended to it a negative sign, okay? And we have to live with it. Now the electron is known to have a negative electric charge, okay? So that is really the foundation of everything that we will we deal with when it comes to electricity and magnetism. This is everything that we do, actually, as a matter of fact, on a daily experience is based on electrons. The reason why you are able to hear me is because at some point the voice that they have in here has oscillations, and those oscillations travel in space and time, and they hit your eardrum, and the eardrum starts to oscillate back and forth due to these interactions between the wave and the electrons in your eardrum, and then at the end it's transferred as a signal, again an electrical signal, to your brain using electrons that come to your brain, and your brain interpret different tones that I'm talking about with different kind of frequencies, and that's what you hear, the different sounds of letters and words and so on and so forth. Same thing is going on with the visual phenomenon. The only reason why you can see anything is because of the electrons in your retina that are responding to the different frequencies that hit your eye from light. And depending on how high the frequency or low it is going to associate a specific, the brain actually is going to append a specific color with that. And that's how you distinguish color, and that's how you distinguish also depth, because again, the intensity plays a role also to give you different variations, for example, of red and so on and so forth. So that's, again, electrons. The only reason why you shake hands with somebody or sit on a chair and not fall through it is because of the electrons of your body interacting with the hand of the other person or with your body in the place where you're sitting. Again, everything that we do day in, day out actually is governed by this particle, the electron. So it's a very important particle that we have to really understand, and this is the foundation of electricity, like I said. Mr. Coulomb, what he did was he gathered a work of a lot of other people before him, and he added to them experiments to confirm a law. And this law looks awfully similar to the law of gravity. There is an attraction between different charges. That's basically what he resolved to. And repulsion, which did not exist with Mr. Newton's law of gravity, between like charges. Okay, so that's basically what the law was saying. Not only that, but actually it drops like 1 over distance squared, exactly like the Mr. Newton's law. The only difference is the constant in Mr. Newton's law was very tiny, was of the order 0.0000010 zeros before the first digit, which is a 6. Okay, I'm sorry, which is a 1.6, so it's a 1. In this case, actually, it starts with a 6 followed by 9 zeros. Okay, so this one, I'm sorry, 9 followed by 9 zeros actually. So it's 9 to the power 10 to the power 9, which is 9 billion. So there is a huge difference between these two forces. That's the only difference between them. I mean, the magnitudes are ridiculously different. I mean, in the favor of Coulomb's law. Coulomb's law is far more, electrical forces are far, far more stronger than gravitational forces, okay? We'll talk about questions related to that later on, okay? And that is going to be the question of the day today. So we're going to talk about that later on. Then we're going to talk about the electric field, which is a key concept trying to describe basically electricity, and that charges create fields around them, and those fields are felt by introducing charges in the area, so they feel that, okay? We're going to explore the concept of the electrical potential. In your houses, you have plugs. You have basically where you plug, you have outlets. And those outlets, they're sitting at a specific difference of potential from one end of the plug, or from one end of the outlet. There are 2 holes usually. There is one potential. From the other end, there's a different potential. If it is one value here, let's say, for example, it's 100 on one side, it's something else less than 100 on the other side. Okay, so if this is 100, the other one is 0. If this is 200, this is actually 100. If this is 300, this is 200, and so on and so forth. So there is this difference in potential. The only trouble with it, and we'll talk about that later on, that this current actually changes places. They switch places. They don't stay where they are all the time. So they flip around. They don't stay where they are. Every second they flip location 60 times back and forth, okay? Then we'll talk about the power source, what makes the voltage, what are the sources of voltages. In other words, how can we make current? How can we make it? That's basically how the idea is. And then we'll talk about the current, which is the flow of these guys, the movement of these electrons, okay? If they move, you have current. If they don't, they don't move. While they're moving, they may experience a resistance by the material. Actually, they will all the time, except if we're doing specific materials which have zero resistance, which are not practical at this point in terms of they exist in our room temperature, but they do exist with no resistance. But most of the time, all materials have resistance, albeit small in some, and very high and probably extremely high in other cases, but there is a resistance. And then we'll talk about Ohm's law, okay? And we will see the two kinds of electrical circuits that we can make. There is the so-called parallel circuits and series circuits. And you will learn that your home is mainly a parallel circuit, basically, because every single plug in your home is the same voltage as the other plug, okay? And then we'll talk about electrical power. And that is basically what is appended to every device. If you look at your laptop behind it, you will see that it tells you specific how much power it requires. If you go to the store and buy a light bulb, it tells you how much power is going to consume. So every single device requires a certain minimum of power to operate, and we'll talk about that. So this is the chapter. This is the chapter in a nutshell. This is chapter 8 for you guys. Okay. Any questions before we delve in? So there is a question of the day here, which we're going to ask today, at least one of them. So again, there are 4 fundamental forces in nature. The first one we saw was the force of gravity. That is force number 1 that is known in the universe. The second force that we're exploring today is this electrostatic force. That's all we learned. I mean, somebody might be tempted and saying, okay, how about the normal force or the force of support? That is actually an electrostatic force, okay? When you push on the surface pushes back because of the interaction of your electrons and that of the surface. How about the force of friction? That is actually an electrostatic force also. Again, it's the electrons interacting between 2 different materials, okay? So what else can you think of? Any other force that we can think, the force of the spring actually is an electrostatic force. It's due to the interaction between the elementary particles of the objects in there. So those are the 2 forces so far really we have seen. I mean, one we have seen, which is the force of gravity, and this one is another force that is that we're going to explore, okay? The others, they're actually exhibition of one of these forces, which is the electrostatic force. So the electrostatic force dominates a lot of the phenomenon on a day-to-day experience. Gravity, though, rules the big objects. For example, the universe cannot be understood without gravity. Why? Because this force actually will be shielded, because we will learn the structure of matter that the electrostatic force, for the most part, cancels each other. Okay, it doesn't really is not, if you wish, apparent that because it cancels one another. And like gravity doesn't cancel, it's always adding. So albeit it's very tiny, but overall, when the object is big, like for example, the Earth, it becomes big and it influences our daily experience, at least apparently more so than the gravity and than electrostatic force, because that's what gets us tired at the end of the day is gravity, okay? So it acts on all particles. For example, and you have to have something in order to play this game. You have to have a charge. Okay? For the first one, you have to have a mass. And which one doesn't? All objects have mass. Okay? Don't tell me energy is not an object. I'm talking about masses. So almost everybody plays the game of gravity. This game, though, you have to have a charge in order to play it. And since there are at least 3 elementary particles that we know of, at least so far, electrons, they're allowed in, okay? And they play with one color, which is the negative color, okay? So this is one team. Another team that is allowed in are the protons, okay? And they're allowed with a different color. We gave it the positive sign, okay? That's what we decided to do. And then there is another terms of another particles which are called neutrons. Those guys, they don't have a charge. So these guys are excluded from this game. They don't play this game, okay? There are 4 forces in nature. The other 2 forces are the so-called nuclear forces. One of them is strong and one of them is weak, in which case you have to have different properties to play it. All 3 guys, they play it, including neutrons in there, okay? So the neutrons are allowed for another game, not this one. And in terms of forces, in terms of gravity, they all 3 play it, okay? Although the electron is so tiny, its mass is so tiny that it hardly participates in the game of gravity, okay? But it plays a major role in this case. As a matter of fact, in daily experience, it is the dominant role in terms of electrostatic force. Okay. So the fundamental properties, like I said, people, when they were experiencing with it, like charges repel, okay? When I say like charges, either negative, negative, or positive, positive. They always repel. This is what we have noticed, okay? And like charges, they attract. Okay, these two, they come to one another. Okay, so this is one of the fundamental natures of that we experience with in terms of this this force. Okay. Okay, this is a model of the atom. This is not how the atom look like. Okay. This is basically a representation of how the atom look like. It has a nucleus, and a nucleus is made up of what I called already neutrons and protons. Neutrons are neutrally charged. They are not allowed in this game. Okay, they are not part of this electrostatic force. They may do other things, and we will later learn what they are, and they play a critical role actually in that one. And there was no no neutrons, life probably would not exist the way it is right now, because everything will fly every which way possible. So that's not, so they are actually part of the gluing of the nucleus. And then we have the electrons. The electrons are in the outer shell. There are 2 types of electrons in the electronic structure of the atom. The ones that are in the outer shell, those, in the case of the so-called conductors, they can move, okay? And those, they participate in the actually currents and things like that. Those are in the inner shell. They're actually much more bound to the nucleus than the ones in the outer shell, and they're actually not allowed to play. So all electrons, they do, except the ones that are actually outside, they actually can play because they can be easily extracted and easily moved. Those are the ones that play the game of the electrostatic charge, more so than the ones that are closer to the nucleus. Again, this is a model, okay? This is a model. I cannot emphasize how much it is, because some people, they have that in their minds that this is exactly how the atom look like. This is not how the atom look like, okay? This is basically a representation of the atom and how it looks like, okay? It's not a planet going around the sun where the sun is the nucleus. No, that's not correct, okay? If we do that, then the atom will be unstable. Atom is neutral because of the fact that you have the same number of protons equals to the same number of electrons. So they cancel one another. How many neutrons it has, it doesn't matter, because those, they don't have charges, okay? Same number of electrons. So you have electrons in metals, specifically, the ones in the outside, the outer electrons, not the inner electrons. The inner electrons, they're toast. They cannot budge. They cannot move, okay? The outer ones, they're loosely bound, okay? And as a matter of fact, they don't belong to a specific atom per se. They belong to a community of atoms, every single one of them. So if one of them is basically somehow pushed around, the atom will borrow the one from next door, basically, because it can. And the one that lost its electron will borrow one from the one next to it, and so on and so forth, until at all times, even in that case of the metal, while current is flowing through it, it's still neutral, because it can do that. the minute one electron leaves for one reason or the other, it grabs another one from the next door, next door, next door, and every single atom will stay neutral, okay? They can move freely because of that, and they can flow. So if I pump, let's say, for example, this is a metal, okay? And if somehow, for example, I remove one electron from here, while in the same time I push another one in here, so this atom will borrow the next one door, the next door, the next door, next door, and next door, next door, and everybody will borrow from his left neighbor until this guy takes the one from the source. So at the end, the metal stays the same. But in actuality, what I have done is I have moved an electron from here to here. That's how actually currents work, okay? That's how actually batteries work too. Batteries, what they do from the cathode, basically, they have negative charges. So they take that negative charge from one side and they push from the other side the positive charge, which is in this case, they grab the electron from the other side, and you have electron, the net effect is moving around. It looks like it's moving around, but all of the atoms basically are just pushing things around between them. So in other words, a battery takes one electron from one side and provides for another one from the other side to the metal. That's all, okay? So again, this is the ionization processes. There are two kinds of materials. There are so-called conductors and insulators, okay? Conductors are the ones I was talking about earlier, the ones that can freely have electrons available to be moved whenever we want to, okay? Case in point, metals, for the most part, are good conductors, okay? And then insulators, you can do that easily, okay? You take one electron from the atom, somehow, from one atom, that atom has no way of grabbing another one from the next door neighbor because each atom is actually closely guarded by its own atom. So if you somehow magically remove one atom or add another electron to it, so now it will be saturated with, it already has electrons, now it's going to be negatively charged. It cannot push it to the next door neighbor, or the next door neighbor cannot grab it because it has its own and it's happy. So that electron will be stuck there if you add one. Or if you yank one of it from one of the atoms somehow, then that atom becomes positively charged because now there is an imbalance between the nucleus and the atom, but it cannot go to the next door neighbor and ask for a replacement because the other one is safely guarding its own. Case in point, for example, rubber, wood, air, the one that we have in here, because the air, the same thing. You cannot easily shake its electrons from the atoms of the oxygen or nitrogen that it's made up of. So that's basically what the air is. So you cannot do that with it. It's an insulator, in other words. Okay, so sometimes you would want conductors, sometimes you would want insulators. And that is really the main difference between. So materials that allow easy flow of charges, outermost electrons of atoms attract loosely and are easily dislodged. So that's in case, for example, in metals. Innermost electrons are still strongly connected to the nucleus. So even in the case of metals, there are not all of their electrons that are free for grabs, okay? Only the outer shells one. The ones on the side, no, you cannot take. That is safely guarded. Those are safely guarded. In the case of insulators, they are greedy. They don't give anything, or they don't take anything. I mean, it's very hard to do that on them. You can, and that's exactly what's happening with lightning. You can move charges inside an insulator, provided there is a huge voltage difference. For example, case in point, the case behind me, the picture that you look at it in here, that is actually lightning. That is actually current flowing through air, which is an insulator, okay? So you can force charges through it. So you can still do that, okay? And that is the breaking point of any insulator. So there is a point where which even those, they will give in, okay? For the case of air, it's about 3 million volts. So when you see a lightning going through the air, you know that the voltage difference between the clouds and the ground has at least reached 3 million volts. Probably it's more. So That's basically what the difference is. But for small volts, like 1,000 volts, 100,000 volts, you can't see lightning. It's not strong enough for it. So when you brush Fido's fur and scrape electrons from it, the charge of Fido is going to be, what is it? I have in here a rod. I grabbed it from Amazon. Actually, I grabbed a lot of things from Amazon. Okay. This is an insulator. This is an insulator by itself. I have a piece of paper in here. I don't know if you see it. I made it from the one of the papers next to me. I cut a little bit of it because I didn't want to. So right now, this does not grab it. Okay. But if I rub through this on hair, which I don't have much of, sorry for that. Some of you probably can do this. I'm going to rub it against my clothes, okay? So I'm going to rub it, and then at some point, I'm going to grab the same thing that I couldn't grab earlier. If I did not rub it enough, okay? Oh, it fell off. Did not fly all over. I guess I need more. How about this one? It's trying to come out, but not as high as now it is coming up. Okay. So here is the question of the day. Okay. I know, of course, you know the answer to the question. Do you guys know what the answer to the question is? So the piece of clothing, basically the equivalent of the Atfel, the piece of clothing that I rubbed this neutral object on it, grabbed electrons from it, charges from it. So what happened to the piece of clothing? Which charge it is, like the fur in this case? So the charge must be positive. Correct? Yes, so that's correct. So basically the charge that was left in there, because now I have an excess electrons in this one, so that means this is grabbed electrons from the other one, so the other one is positive. Okay. So why was this one grabbed? This one was neutral to begin with. I couldn't grab it to begin with. Now I canceled the charge in this one. I cannot grab it unless I rub something on it. So what happened to this one? Why was it being pulled? The answer is coming, okay? So that's the question. The answer is coming down the road, okay? Does anybody know right now if you read through the chapter? Here's the question. Here's the challenge. This one is neutral by itself before rubbing, because right now I'm trying to pull it. It's not coming up at all, okay? If I charge this one, hopefully it charges enough. I'm using against a that's not a blanket. What is this?
Static electricity.
Yeah, I'm creating static electricity. You're right on that. But the point is, this one is neutral. I couldn't grab it earlier, but somehow now I can grab it. Remember, I have to have a charge. Right now, it's not even being grabbed because I didn't. I don't want to touch it with my hand because my hand is a conductor also. And that would neutralize the charge. Can I get charges from that? No, I'm not getting charges. Okay, try it again. It should work at some point. Okay, oops. This thing is too big. Maybe I should make a little less of it. Okay, oops. There it is. It fell off now, okay. So what happened in between them? Yes, I put charges on this one. I put negative charges on this one, correct? By rubbing it, basically. I grabbed the electrons from the surface of this piece of cloth, okay? But the paper did not have a charge to begin with and does not afterwards. So what happened to the paper? Okay, the answer is coming then if you didn't read through the chapter, because it should be somewhere around the end. You're right. I mean, electrostatic forces, that's correct. But the electrostatic charges that I built only on one end. I didn't build it on the other side. Okay. So let's continue with this, and we will see the answer somewhere in one of the slides. It's coming down the road.
Is that experiment kind of like rubbing a balloon and then holding it up to your hair?
Okay, that's correct. So what is that supposed to mean? There is a word for it, right? That is correct. You nailed it, but I want the word now, the key word for it.
Oh, all I can think of is like static electricity. That's all I'm thinking.
Okay, it's one of the slides coming down the road, okay? You can see through it and you will see exactly what that phenomenon is called. I mean, there is no question about the fact that I put charges on this rod. There is no problem with that. I can understand that by simply saying I removed the electrons just by rubbing basically this thing long enough. So I put charges on it. That's fine. But the question is, what happened to the paper? Why the paper now is all of a sudden, if the paper was zero charge, okay? If the paper had zero charge to begin with, it would not be attracted to any negative charge or positive charge, doesn't matter. Because you need a charge to play this game. And this paper did not have any charge whatsoever to begin with. So it's similar to the balloon. The balloon, when you rub it on your head, on your hair, or anything like that, now it has charges. You put it on the wall was neutral. But all of a sudden now, the balloon is sticking to it, okay? So that's where the question is.
Transfer of electrons.
I'm sorry?
Is it a transfer of electrons?
To
like
the wall?
friction?
Yeah, we transfer to the electrons from whatever we rub the balloon on to the surface of the balloon. So the balloon has charges. I have no problem with that. And the wall does not have charge. It was neutral to begin with, and it's neutral still afterwards. Okay, because I put anything next to it, it's still neutral. But somehow the balloon now sticks to the wall, or in this case, the rod attracts the paper. So the answer is somehow down the road. Okay, it's one of the slides down the road. So again, charges are conserved quantity. This is a key concept in here that that is one of laws of nature in that no matter which phenomenon you have, charges are conserved, okay? So if you have a bunch of charges that are coming to a junction, and let's say, for example, 10 of them, and you know that 6 of them went this way. So how many would have gone to the other side? If 10 of them came in and you counted 6 moving to the left. So how many went to the right then? I brought in 10. Let me draw the graph in here. So I brought in 10, and they split, and I know 6 moved this way. So the question is, without doing any measurement, how many went to the other side? So this is the incoming charges, that is the outgoing charges, and this is the other outgoing charges. How many? Let me show you the picture again too. Because we say that they're conserved. So if I counted 10 coming, and I know 6 left from one side, how many would have gone from the other side? That's correct, okay? So 4 must have gone through this side, okay? So if you have a splitter, for example, for the power, for example, what do you call them? Those power splitters, those cables that you use for to split power. And you know a certain current is flowing one side, so you know basically, and if you know how much went through one side, you know how much went through the other side. Same thing, for example, for the flow of water. So if there is a certain flow and a certain amount is flowing from one side and half of it is going this way, you don't need to know about, you don't need to do measurements on the other side. You know the other half went through the other side. Because if there is a center amount of water is flowing in this volume, and it splits, let's say, for example, halfway, then half is gone this way and the other half is gone to the other side. So that's similar. So this is a conservation of matter in here. So matter is conserved in the case of water. Conservation of matter, because the atoms don't get created or destroyed in the process just because. As long as there is no sink in here, if you poke a hole in the thing in here, yeah, it may have an imbalance. The same thing. If there is no process in here where charges can get destroyed, and there is none, then you know for a fact that if 6 went one way, the 4 went to the other side. Okay. The fact that I removed the electrons from this clothing, that means that let's say, for example, I remove 10 and put them on my rod. The other one has missing 10. So again, charges are conserved. This is one of the fundamental laws of nature, and it plays a major role in circuits. So when you do a junction, this is called a junction. When you make a junction in a circuit, you know that this law works. Actually, this one has a name. It's called Kirchhoff's rules. It's one of the main rules to build circuits. I mean, engineers, they deal with this law all the time, trying to build circuits. Okay. This is Coulomb's law in its glory. Okay. The product of the two charges, like the product of the masses. Let's compare this one to Newton's laws. It says G. Come on, can I write G in here? This is the capital letter G, okay? This is 6.67 times 10 to the power negative 11. Capital G times mass 1 times mass 2 divided by the distance squared, d squared, okay? So the d squared is in both the same. The masses are the same, okay? The constant K in this case, this is the constant whose number I gave you earlier is 10 billion or 10 to the power 10. This one is 6.67 times 10 to the negative 11, which is a very tiny quantity, okay? Big G was needed by Newton to make the units correct and to explain the apple, okay? Big K was needed by Mr. Coulomb to make the units correct also, and to explain also some of the electric phenomenon that he has in there. That's why he came up with this number 9 times 10 to the power 9. And the units must match so that the product of the charges, which are going to be in coulombs, people honored him with this name later on, divided by the distance squared, which is in meters. And in both cases, the distance squared is the same. So there is a similarity between these two fundamental forces of nature. These are some of the big similarities between them, and one of the distance squared, which is really a puzzling thing. One of the things that people ask about the quantity G itself, I mean, quantity, this K, by the way, has to do with something else, okay? But G itself is one of the mysteries of the universe. K has to do with the medium that you do the experiment in. If you do it in vacuum, it's one value. If you do it in water, it's a different value. If you do it with different insulator, for example, with rubber, it's a different value. So that is actually a property that has to do with the medium itself, okay? But G is one of the mysteries of nature. The unit charge is a very small quantity. That is also another property. Not only it's conserved charges, but it comes in a discrete number. It's always a multiple of the charge of the electron. So no matter how much charge you're talking about, it's always a specific integer of electrons. It could be 100 electrons, and each one of them is 1.6 times 10 to the negative 19, or it could be 3 billion of them. Each one of them is 1.6 times 10 to the negative 19. Or it could be lack thereof of this electrons, meaning it's the charge of the proton, which is the same value, which is another mystery of this universe, why the proton specifically has the same charge as that of the electron, which is really a mystery. There is no reason for them to be. Not only that, every single electron in the universe has the same charge. So these are some of the mysteries that scientists are working on. I talked already about that constant K. This is its numerical value, 9 times 10 to the power 9, a Newton meter squared per Coulomb squared. The reason why we chose the units in here so that this force can be measured in newtons. Like signs repel, and like charges attract. This does not happen with this Mr. Newton's law. It's always attractive. Gravity always attracts because we have never seen negative masses. The only thing that we know is positive masses. All masses are positive. Therefore, this law is always attraction from that of Newton. However, that of Mr. Coulomb can be attractive or can be repulsive. If one of the charges is zero, this is zero. So there should not be an attraction or repulsion, which brings me back to the case that I was talking about earlier. This one is neutral when I started with it, and this one has a charge, but somehow there was an attraction in it, okay? And it has to do with the slide that is coming down the road. So the difference and similarities between them, I already stated them. Both can act at objects with no direct contact. The Earth and the Sun never touch, but they experience attraction. And the same thing with charges. So this is basically what some of the similarities. They drop like 1 over distance squared, both of them similarly. And there is a big difference between them, and that is their strength. One of them is super strong compared to the other one. And this is similar to gravity in this case. According to Coulomb's law, a pair of particles that are placed twice as far, of course, you double the distance, you square that double, that means it's 4, but you divide by 4, so the force should be 1/4 strong. It's going to drop. You double the distance, sorry. No, you double the distance, the force is 1/4 as strong. Yes, it drops by 1/4, okay? So here is where the answer lies to the dilemma we were dealing with. Although this guy is neutral, okay? What happened in it when you bring a positively charged rod, a negatively charged rod next to it, it's going to pull the negative charges one side, leaving. So this is how the paper was before I put next to it the rod, okay? The minute I bring the rod next to it, the electronic cloud moves closer to the cloud, which means, because it's less mass, so it moves easily, okay? So it moves closer to the negative charge, which means that the positive charge, which has more massive, doesn't move as much. It has high inertia, so it stays behind, okay? Sorry, did I say it backward? I said it backward, okay, I'm sorry. I bring the rod next to it on the other side. So the rod actually is put in here because it has a negative charge to bring it. So this is the rod, okay? So in this case, because it's negatively charged, it's going to repel the negative charges, and they're going to move this way. This one hardly budges, okay, because it has tremendous mass, okay? So it looks like it's moving this way, but it's not going to move at all because it's mass. So in this case, the paper will stick because of this closer positive. So this like acts like a positive charge from one side and a negative charge from here, and you bring the rod next to it. So this phenomenon is called polarization, okay? So that's the answer to our problem. That's how we understand it. Now the same thing happens with the balloon. So if you bring the balloon and you rub it against the surface, now it acquires negative charges, you put it next to the wall. In this case, what happened? The electrons of the wall move away from it, which means that leaves closer to it the positive charges from the atoms of the wall and make it so that it sticks there. And only in that region. If you touch the wall anywhere else, it's still neutral. Okay. Bring another balloon that is not rubbed in the same time and one that is rubbed and put them next to the wall. The one that is rubbed will stick to it. The other one falls in because of the fact that one of them is the one that causes the polarization next to it. The other one still attached to a neutral wall, in which case, although you have no, because you have no charges in it, it's going to fall. The other one has charges, it's going to induce this phenomenon of polarization, okay? So that's the answer to the question. Does this make sense to you guys?
Yep.
So that's the answer. That's what happened, okay? So the wall stays neutral. the paper stays neutral. Remember, you cannot create charges out of nothing. Okay, the fact that now you have negative charges next to the paper, that induces polarization in the paper to make the positive charge of the paper closer to the rod, and that is really short-lived because that interaction is very weak because you still have the negative charges on the other one repelling the wall, repelling in other words, when those charges in here moved away, although they moved away, but they're still there. And that's why this is short-lived, okay? Short-lived to the point that it's going to fall. So it's not a strong interaction. And like when you have pure charges against pure charges, that is going to be pure attraction. Here is what we were talking about, okay? So the negative charges will repel the negative electrons in here, and in a sense, create, because these guys stay in their place. They're not attracted, by the way. They stay in their place. So now near the balloon, this appears to be attraction in here between these two. But there is still repulsion in here. Give it a little bit of time and wait for it another 15 minutes, 20 minutes, 1 hour maybe. This balloon will fall ultimately because these guys still work against it until they cancel it, okay? Until they come closer so that this thing will fall. One of the concepts that we need usually is the electric field, okay? Electric field is a phenomenon that is actually measured using a test charge. And test charge, when you bring it next to a near a positive charge, will always be attracted because the test charge is a, excuse me, it's positively 1 Coulomb charge. So that's a hypothetical charge. Of course, you cannot carry 1 Coulomb in your hand. It's going to burn you. It's a big charge. 1 Coulomb is a huge number of electrons or lack thereof. So, but assuming you can put it near a negative charge will attract that net Coulomb. Hence, the sign of the electric field pointing toward the negative charge. And the strength of it depends on how much negative charge you have. The more negative charge you have, the stronger it is. And again, it depends also on 1/distance squared. This is the representation of the electric field. Had you moved with a negative charge in 1, 2, 3, basically 8 locations around it, okay? Now you agree with me with the following rule. If you double this charge, you cannot do just 8 locations, you have to do 16. That is basically the convention with the magnetic field, okay? That if you agree on a certain number of field lines, in this case 16 per charge, now if you double the charge, you have to double the field lines. If you cut the charge by half, then you have to only represent it by four lines. So basically, there is a convention that talks about the density of field lines versus the strength of the electric field, namely the charge that produced it. In this case, it's a negative charge. Now, this is a single charge, which is positive, which is the opposite of the first one, and this is represented actually by more than 16, more than 8 charges, okay? So you have 1, 2, 3, 12 basically field lines going around it, okay? So if I go with my convention, this has only, what, 8, this one has 12, that means this one is a time and a half stronger than the first one. But that doesn't matter also because I may have come up with a convention in here for the same charge, and I have to stick with my own convention then. That is in terms of the intensity. In terms of the sign, now because if I bring a test hypothetical charge in here near it, it's going to be repelled. It's going to be moved away. That's why this is an outgoing field for a positive charge, and it's an incoming field for a negative charge. Now, if I have what is called a dipole in this case, then the electric field will leave the positive charge and terminate in the negative charge. Leave the electric in different curves, of course, okay? Depending on which path we take. Those are so-called field lines. Now, at some point, it's going to go in here, go around basically this, the entire state of California and come back, okay? At some point, it's going to actually go around the entire continent and come back, the entire US. And at some point, it's going to go through the entire universe and come back to the other end. But always, the field lines emanate from positive charges and terminate in negative charges. This is a dipole, okay? This one's, there is no other charge next to it. The dipole is made up of usually same charges, but different size. Okay, this one is a single charge by itself. Single charge by itself, the electric field will always emanate from it and end in infinity. They don't end at all. You go toward the edge of the universe and they still continue up past that point. Same thing with this one. They emanate from the other end of the universe and they terminate into the negative charge. So you go to the end of the universe to find where the field lines are coming from, and you will find that they're still coming past that point. Albeit they're weaker though, because the further you are from the point charge, the less dense they become, the less, and it drops like 1/distance squared, if you want to call it in that sense. Now here is another invention that we work with in KC, which is a region between two plates. And between two plates, one of them is positively charged and one of them is negatively charged. The field lines will leave the positive plate and end up in the negative plate. And in this case, it is trapped in that region, as a matter of fact. Ignore the edge effect, because in here, they don't look as straight toward the bottom or toward the end. But in between them, they're actually straight field lines, okay? So if you put an electron in between them in here, that electron will be repelled by the negative plate and fall into the positive plate, okay? If you put a proton in here, that proton is repelled by the positive plate and attracted to the negative plate. So if a bunch of charges in between these two ends of this, this device, some of them will fall on one side, depending on their sign, and some of them will fall on the other side. So that's following the field lines. Each one of them follows the field line. Same thing in here. If I put a charge in here, that charge, depending on its sign, if it's a positive sign, it's going to be repelled by the positive end of the pole, the dipole, and it's going to end up in the negative charge. But if it's a negative charge to begin with, it's going to do around. It's going to go against the field lines. So negative charges will always act against the field lines. In this case, they move this way. In this case, they move this way. In this case, they move this way. Positive charges will follow the field lines. Whichever is pointing, they point with it. So that's basically, in a nutshell, what field lines are. I mean, they're real phenomenon, because in the Van de Graaff machine, if you stand next to it, you build up charges in your body, including your head. And in that case, field lines basically will follow your hair. So this is a real phenomenon, okay? Has any one of you experienced the Van de Graaff machine? I mean, we have, I think, or must have at least a couple of them on campus. Did you guys do it in Science Center or anything like that? No? Nobody? They're fun. Okay, at least Jacqueline experienced it, okay. Okay, they're fun, okay. If we have a chance to go back on campus, usually I bring them and we demo them, and it's fun. Okay, you build charge. Nowadays you don't do it, man. You put just in the plug, and it's going to pick up charges and build it and put it on this metallic spherical, basically conductor, and then you stand on a neutral, basically platform that to make sure that you don't conduct electricity yourself and become a current through it. So all the charges that are actually coming from your the conductor goes to your body, and then you will see your hair actually starts with your hand, and then your the entire body. You can feel it actually before it starts to be apparent in your body. I mean, for me, it's not going to be apparent because I don't have much hair, but if you have it, then you will experience it much more. It's a fun thing, okay? You wonder what happened afterwards. Well, we have to cancel the charge in your body through another mechanism before you step down. Otherwise, you will be electrocuted. I mean, it's not much charges on it. It's just like a small tip. Okay. Which brings us to the electrical potential. Now it's 9:30, and we are midway. Okay. So the electrical potential energy is similar to the potential energy for gravity. Basically, you take a mass, you put it at a certain height, cut the string. In this case, it's going to release that potential energy into kinetic energy, which can do work for you, okay? Same thing in here. You take a charge and you put it near another charge, depending on the signs in here. It's going to be either attracted to it or probably repelled from it, okay? So if you have a charge next, if this both were positive, you really have to hold it in place. If you let go of it, then it's going to escape toward infinity, and it can do work for you. It can move things around for you. It can do the same thing like the other one. As a matter of fact, this is the idea behind motors. That's electrical motors, and that's exactly how your computer is heating, and that's why everything works the way it works, okay? Because of this principle that you take potential energy now, which is in the form of electrical energy, electrostatic energy, and you convert it back to work, useful work that you can do work with. So this is the idea behind electrical motors, by the way. Okay, so the same thing. I mean, we're talking about the analogy with the negative charge in this case because it looks attractive with a positive charge. Whereas in this case, both charges have the same sign. So you really need to have a force to keep it in place. The same thing in here with the spring. If you push it back, you need a force to retain it in its location because you have built potential energy in it too. Or pull it in this case, similar to that, it's going to attract backwards. So this is the concept of the potential, electrical potential. Again, we're talking about energies, so every time we mention energy, it's measured in joules as much as kinetic energy, because if I have an electrical potential energy, I can move it to potential kinetic energy, which is in joules, so both of them have the same units. The test for us is usually kinetic energy. Again, I already mentioned the fact that you do useful work with it. Now, electrical potential, which is related to the electrical potential energy. The potential, the electrical potential energy can do work for you. Electrical potential energy actually can result in a force, and that force can do work for you. Okay? The electrical field, the electrical potential, I'm sorry, by itself, the electrical potential, not energy, electrical potential only by itself, can give you actually an electric field E. This one can give you a force. This one can give you an electric field, which again, you can use to do force with it. So from here, you bring a charge in it and it's going to generate a force for you, which can do still work. So there is that step in here, relationship between the electrical potential and the electric field. They're related to one another. Difference between the electrical potential and the electrical potential energy is this charge in the denominator. That's all. So 1 volt, which is the unit for the potential, is 1 joule, which is the unit for the potential energy, for 1 Coulomb. So if you take 1 Coulomb charge and you put it across 1 volt, that's going to give you 1 joule. That's basically what that means. You do 1 joule work. So basically 1 apple moving 1 meter. 1 apple that weighs 100 grams moving 1 meter. That's exactly what that means. 1 apple, which is 1 Newton, which is 100 grams, which is 1 Newton, when you move it 1 meter, is also 1 joule. So 1 joule also, you can think of it similar to the apple and the 1 Newton over 1 meter, is that now it's 1 Coulomb forced to stay between 1 volt. The fact that you have 120 volts in your house, which is the effective voltage that you have in your plug, that amounts to, if you put 1 Coulomb in it, okay, across it, that you have consumed 120 joules in your house. So there is that connection between a joule and the voltage. Okay, they are not the same, but they're related. And the difference between them is the charge. That's what conversion between them. The same thing, a force and work are not the same. Force and energy are not the same. You need the force to do work over a distance, okay? That is an analogy in this case. Again, the fact that you have 5,000 volts doesn't mean much unless you see how much charges this 5,000 volts do work for you, okay? So if you are standing on a neutralizing surface and you're basically put 10,000 joules in your body, like for 10,000 volts, yeah, 10,000 volts, for example, in your body, not 10,000 joules. 10,000 joules to be too much energy in your body. It's fine, as long as the charges are not moving, okay? But the minute you step out of the neutral zone and you start to, for example, touch a wet surface where the currents start to flow, then that 10,000 volts can result in a tremendous amount of energy that can result in serious damage to your body or probably your heart or something. So don't do that, okay? Electrical potential energy is measured in joules. Electrical potential, on the other hand, is measured in, I already stated that, volts. Okay, we're running short of time, so let's get some of the questions in here. The other question in here, when you buy a water pipe, oh, this is an interesting topic, okay? You go to Home Depot and you tell them, I need a pipe for my conduit for my water, basically, thing, and they tell you, here is a pipe for it. They usually sell you a pipe for the conduit of the water, but they don't tell you the water with it, okay? You have to actually go to the water company and tell them to deliver the water to go through the conduit. Let's say, for example, the water company has only 10 liters of water, and if you consume the 10 liter in your garden, wherever that is, or your shower, that's it. The water company is run out of water, and you have to find another source of water. But if you go to Home Depot and you tell them you want copper, for example, for your electricity, that comes actually with the charges in it. So the copper wire comes with the charges in it. So as if you bought the conduit with water already in it, okay? But doesn't work that way for the water. It works this way actually for electricity. Now you go to the power company and you tell them, okay, I need current through here. So what they do in this case, they provide the voltage difference between the wire, so that to move your electrons that you bought from Home Depot from one end of the wire to the other. What happened to them when they reach the other end? The power company grabs them and replenish the conduit that you bought from Home Depot. That's all. So you still end up with the same amount of charges that you bought to begin with from your power company. So that's an interesting analogy between the two to keep in mind. So the power company does not provide you with the electrons, provide you just basically with the difference in potential, 120 volts, that's it. So, unlike the water company that provides you. So the answer to this one is supplied when you buy copper, electrons are already in the wire, okay? So again, I just made the fact that the power company basically provides you with voltage. Also, when you go and buy batteries, they provide you also with the so-called electromotive force, the force that is necessary to move charges in your circuit. So, for example, you buy a 1.5 volt battery, which is a typical battery, 1.5 battery between one side and the other side of the battery, which is this long battery. There is a potential difference, so this is the label positive, this is negative, of 1.5 volts, okay? So that is really what you're buying from there. You're buying that power, that difference of them. And as long as it has what it has, which is usually chemical processes inside, it can always replenish the charges that you lose from one end to the other side. So if you put, for example, your computer in here and you plug it in here, so what happened in this case, the electrons start to move from one end and end up in the other side. Now, the minute the electron comes in here, the battery, what it does, it drags it to the other end. That's all. That's all it does, the battery. That's its job. That's its really power. That's what you're buying. What you're buying in this case, its ability to move. Every time a charge lands up in here, it's moved in there. Negative charge, that is. I mean, we say by convention that the current flows against the negative charges. So if you put an ammeter there to measure the current is actually going this way and coming that way. It's against the electrons. Again, I said that because of an accident that happened in representation. So with the minute that a charge ends up in one end of the battery will drag it to the other side. And why? Because the battery is still good. The minute the battery starts to run out of energy, basically it will not do that as good. So in that case, that's the time when you need to go back to the store and buy another one. Okay? So as long as there is still chemical energy inside the battery to do that, the battery will function, will do its job. The minute the battery runs out of that chemical processes, the mysteries inside of it, whatever works in it, to do this, that's it. That's the time when you go and give up and basically grab another one. Same thing with generators, for example, of power. And so the analogy with the battery in this case, again, for the flow to work, you really have to have a difference in potential, okay? And the case of the battery is 1.5 volt. I mean, the typical AAA or AA batteries. So 1.5 volt, the difference between the two ends. So if a charge falls in on one end, so if you connect the two, the charge, actually the negative charge that is sitting in here, will go and end up in the other side, false. The trouble with that is the battery, if it's still good, it's going to move it against its own will to the other end. Because there is a bunch of negative charges already here. And there is a bunch of positive charges in here. That is basically what a battery is. So the minute you connect them through your computer, okay, whatever device you want to connect, now the electrons, they found a way to go and meet their positive parts, and they're supposed to be happy there. But the battery has a secret. And that secret is something outside of the physics, which we're going to call chemical processes. And that is the one that forces the negative charges to leave where they're supposed to be and end up where they really don't want to be. So if you have a microscope and look at those electrons in here with a magnifying glass, you will see them crying actually, because they don't want to go to the other side. That's what the battery does. Okay, it moves them against their will. As long as it has still some juice in it, the minute it runs out of juice, they will end up in where they want to be, and nothing the battery can do will force them to the other side. That is the time when you go and get a new battery. You guys understand how electrical circuits work with this analogy? Yes?
Absolutely.
Okay, Sherry. So hopefully with a microscope, and Emmanuel and everybody else can go and look at those electrons, and you will, believe me, you will see them crying. They don't want to be to the other end because they know there is a bunch of negative charges on the other side. Okay. Okay. So again, this is another analogy for circuits. I mean, we always give the analogy with the flow of liquid or water. This only can go so much, okay? I think you have a battery in here. Again, you have, if this is a negative and this is positive end of the battery, when you connect them, when the switch is closed, when you turn on the switch, the charges start flowing this way, okay? The thing with it is with an ammeter, the one that measures the current, is actually you will see it moving to the other side because we chose the sign for the electrons to be negative. So we call this is the direction of the current. Okay, and this is the direct, which is the current I basically. We still have a few minutes, so let me get some, these are still more pictures of what I was talking about. This is the current. Let me get into another idea in here. Okay, that was a DC current. What you have in-house is an AC current. It's an alternating current, okay? So, but it has an effective effect similar to the DC current. So basically at the end, the charges will move one way. I mean, the current is on time is this way. The current is on the other side this way. But at the end, what matters is really the power. What is your device is consuming in power? And they behave more or less similar. So when you hear them saying it's 120 volt, it's actually going up and down between positive 170 and negative 170 volts all the time, oscillating. Effectively, this looks like 120 volts. How is 170 related to 120? It's a matter of averages. And it's not exactly the between them. It's not the average of the current that is really matter. It's the average of actually the square of this quantity, because that's where the power comes in. It comes in the square of the voltage, not the voltage itself. Because the average of this quantity is 0. But the average of going between 0 and 170 all the time, That is about 120, okay? Not midway, somewhere a little above that. Because a lot of the time it's actually thicker than this separation in here because of this oscillations. That's why the average is not sitting at 170, but a little higher than that. So that's basically a distinction. So when you hear them saying it's 120 volts, you have to understand that the voltage actually changes up and down. The electrical resistance, I mentioned the fact that all materials exhibit resistance, okay? And good conductors, they have less resistance than poor conductors. Or insulators. Insulators, they have very high resistance, okay? Which brings me to the last law, the one that we deal with in terms of electricity, which is Ohm's law. Ohm's law says the current in a circuit is proportional to the voltage and inversely proportional to the resistance. So the resistance acts like a mass in this case, except the mass in this case is the resistance of the object to the current, whereas the current acts more like the speed, okay, and of the charges of how much fast they are moving. So it's not similar to F equals to ma exactly, because A is the acceleration, not the speed in that case, okay? And the voltage is not equivalent to the force in this case, because in the case of F equals to ma, A is the change in speed, not the speed itself. In this case, it relates to the speed of the charges versus, or the flow of charges versus the actual cause of it, which is the voltage difference, which is 120 volt or 1.5 volt, or no matter 12 volt for the case of the battery of the car, or so on and so forth, okay? So this is the law that ends in this case, this whole chapter. Let me see what else is in terms. Okay, I mentioned the fact that there are two types of circuits. There are series, you can put an object one next to one another, and there are parallel circuits. There are some technical differences between the two. One of them is useful for making the voltage the same everywhere. That is the case of houses, okay? There are the cases where you want the current to be the same. So here, same current. And you put them one next to the other, okay? So the lighting in this case would depend, of course, will be the same. Depending, of course, on the resistance only. If they have the same resistance, they will all light the same. In this case, the voltage is the same. Okay. But the current is different. So the current is different in this case. The voltage is the same. Here, this current is the same. The voltage is different. So that's the difference between the two. Any circuit is a combination of both, actually. Any circuit. So just to go back into the houses, this is how a house looks like, okay? All of the devices, the lamp, the heater, and everything are sitting in the same voltage at home, okay? That is a parallel. And the breakers are actually usually due to heat, they break the circuit in two. Okay, this is in a nutshell the chapter. I know we still have about 5 minutes or something. I want you guys to go back and make sure that you're ready for the exam on Tuesday, okay? By the way, you will be receiving an email from the campus, I think, to improve instructions and things like that. So please fill the survey as much as you can and respond to that survey from the campus. It's from the college to everybody, basically. They receive a survey similar to what you guys are willing to receive. They pick some subjects specifically, and they told me that to inform you guys that you might be receiving it very soon, okay? Sarah, did you already receive it?
Yeah, something like that. Probably for another class.
Okay, so you receive something like this one for this class. Okay?
We have a discussion to do
Yes, we do, don't we?
because my computer keeps lagging.
Okay, let me check in here to make sure that we do for this class, for today's class. I mean, I usually don't have to do a lot of assignments during exam times, honestly, because I really want you guys to focus on the exams. And there is for chapter 8, yes, there is a discussion. Okay? So with 5 points. So you know what the question was today, and you know what the answer was today. Any questions about that?
No, I don't know the question because I can't write it.
Okay. Can anybody remind us of what the question was? It has to do with this.
It was about with the like a neutral object, or like an object with a neutral charge gaining like a negative charge, right?
Attracting a neutral object, like for example the paper. Okay,
Yeah.
this one we charge it. The paper was neutral, and somehow they both attract. And we said Coulomb's law requires that both of them have charges. I know this one does, this one doesn't. So how come I have attraction in this case? And the answer has to do with
Charge must be positive.
Or
there is another keyword for the answer. I'm looking for. You can look it up. Okay, let's go back to that specific slide. That's where the answer was. It has to do with the balloons and the wall. Balloons on the wall. Here. So this is the keyword. Okay?
Okay.
polarization.
Yeah, it induces a positive charge, okay, on the wall or on the paper, okay? And that is what is the keyword there. So it's polarization, okay?
Okay.
Got it?
Mm-hmm.
Got
So that is the answer to the prompt. So the question was, you have a charged balloon, for example, and you bring it next to the wall, and all of a sudden, although the wall is neutral, I know that because I can put another balloon that is not rubbed next to it and it's not going to stick. But this one does stick. So what is this one doing? It's polarizing the wall next to it and making it as if it has a charge so that Coulomb's law still apply. Got it?
it.
Mm-hmm.
Does it make sense to you?
Yes.
Okay. So I'll see you guys on, I will be available on Tuesday. Like I said, you don't have to be, but I will be available from 8 to 9:55 in the morning.
Was that the only question of the day?
Yep, that's it. Aren't you lucky
Okay.
today?
Extremely lucky.
Okay. See you guys on Thursday then. Okay.
Thank you.
Okay, bye.
Thank you.
Okay, bye.
Thanks again.
Okay, bye.